Hi, so in this video we're going to start looking at how energy is involved in different chemical reactions, specifically in terms of reaction rates. So we should recall from earlier on in the chapter that temperature has an effect on how quickly a reaction may go. In general, at higher temperatures, you can increase the rate of a reaction. And the reason for this is because in order for a reaction to occur, basically the reactants themselves need to have enough kinetic energy in order to turn into products. Now, as a reminder, kinetic energy is the energy of motion, and at higher temperatures, the kinetic energy is going to be increased for any particle, whether that be in the gas phase or even things that are like solids or liquids, right? At higher temperatures are going to have more movement associated with them. But so the reason that this kinetic energy is kind of required to make our reactants into products is because if we think about just like the relative energy of our reactants and our products, right? Reactants and products are generally pretty stable. So what that means is that they're at like a lower energy state. Things that are at lower energy are like happier, more content. They're less likely to change away from that nice stable condition. So if we do want to change a chemical and turn it into like a new product, right, that is going to require some minor discomfort for a while, right? Basically, making it into some slightly unstable formation momentarily so that it can get back into that stable form. So to kind of explain this, I'm going to take a look at this reaction where we have methyl bromide or CH3Br and hydroxide or OH minus. These two are going to react to form bromide, Br minus, and methanol, CH3OH. But so for this reaction, I want us to kind of think about it in pictures just to kind of help give an idea of what this actually looks like. So right, our reactants here are CH3Br and OH minus. Now initially those two things are separate. So that's shown in this picture, right, of like the CH3Br on the left and then the OH minus kind of coming in on the right. The products are going to look slightly different. We have our bromide kind of separate and then the methanol is like what's on the bulk there. But so right, in order to go from say point A to point B like we have in these reactants and products, basically there's going to be some in-between state where the carbon in the CH3 group, right, that carbon is going to be partially bonded to the bromine and it's going to be partially bonded to the oxygen, just kind of like in this transitional phase right between reactants and products. This is known as the transition state, or sometimes also called like an activated complex. Activated just as in like it has a higher energy. But right, this is again like an unstable species because it has these partial bonds in it. And so it's going to naturally be higher in energy than either our reactants or products that we have in this reaction. To kind of map that out fully, see the energy associated with each of those steps, we can represent that right here in what's called a reaction energy diagram or a potential energy diagram. So this shows the potential energy of our substances as the reaction progresses. So on the left, we begin with our reactants. On the right, we end with our products. And you can see following this curve here, right, that in the middle, that's where our transition state is. And that middle section has a much higher energy associated with it, right? Kind of resembles like a hill, this big bump there, right? It's that bump or the peak of that hill that is where our transition state lies. So from this reaction energy diagram, we can take away a few important things. Most notably, I want us to focus in here on what's called the activation energy or abbreviated EA. This is the energy that it takes to basically reach the transition state from our reactant. Now, traditionally, we think of activation energy as going in the forward direction for our reaction. So again, reactant into transition state. But sometimes we also may consider the reverse activation energy, which is going from products to transition state. These are shown in the graph right here as either EA forward or EA reverse. So these differences in energy, those are different types of activation energy. Now, also in this graph, we'll see reference to something familiar, hopefully, the change in enthalpy or delta H of reaction. This is still just like the overall change between our reactants and products. So we can find the change in enthalpy by just comparing, right, where the energy is for the reactants versus the products, taking the difference in that. Or we can think about it in terms of the activation energies themselves, where the change in enthalpy of reaction is equal to the forward activation energy minus the reverse activation energy, right? Really just the difference between those two EAs, right? That is our overall change in energy for the whole process. Now, in this reaction in particular, we can see that the delta H is negative, meaning that this is an exothermic reaction, but endothermic reactions are going to have kind of a similar look to them as well. So I'll show again right here like another exothermic reaction, say this reaction of NO and O3. So again, we see that like hill shape in the potential energy diagram, and because our reactants start at a higher energy than the products, right, that gives us then an exothermic reaction overall. But an endothermic reaction we can see right here as two NOCl reacting together, right? That has, again, that same hill shape to it, but here now the enthalpy change is positive, so we expect to see the products at a higher energy than the reactants were. Now, exactly how large that hill we see or that activation energy is, that depends on just like how unstable the transition state itself is, right? Some transition states are still relatively stable themselves, so it's a little bit easier to make it over that hill. But for other transition states, right, in order for our reactant to turn into product, it needs to make like a really big jump there. So that would require then a higher activation energy and thus a lot more energy to kind of push it over the edge. Now, measuring like the energetics of different reactions can be a little tricky, honestly, just kind of keeping track of exactly where the energy is relative to our initial or reactant state versus our product state, can be a little bit of a challenge, but there is a way to actually use this relationship between temperature and reaction rate to determine the activation energy of a reaction. So this can be done by studying, right, the rate of reaction and studying the rate constant specifically of a reaction just at different temperatures. These things are related through what's called the Arrhenius equation, which is written out right here. This says that the rate constant of a reaction is equal to A, which is known as the frequency factor, times E, like the mathematical E, to the negative activation energy divided by RT. Now, R here is the universal gas constant, which you guys have seen in previous chapters, like in the ideal gas law and some other applications as well. This is specifically R in terms of joules per mole Kelvin, so 8.314 is the number that we'll use for R there. And then the temperature is, of course, the absolute temperature, so the temperature in Kelvin. All right, so this Arrhenius equation, again, relates the rate constant to the activation energy at a particular temperature. There are like derivations to the Arrhenius equation that can be used as well to show the same relationship. So one common way that we'll see the Arrhenius equation kind of rearranged is like so. So in this, what we've essentially done is we've taken the natural log of both sides of the equation to derive into this equation that says the natural log of the rate constant is equal to negative activation energy divided by R, and then all of that times 1 over the absolute temperature, and then plus natural log of that frequency factor A. The reason that this derivation is helpful is because it may not look like it right now, but this does actually resemble kind of a line equation, right, of y equals mx plus b, where y is the natural log of k, m, or the slope, is equal to negative EA over r, x would be 1 over t, and then b is the natural log of a. So we can kind of use this quality of the Arrhenius equation to kind of plot out maybe a line of different rate constants at different temperatures, or specifically different natural logs of rate constants at 1 over the temperature. And we can take from that, right, a couple of important things. We can find the activation energy just in terms of whatever the slope is. And we can also find the frequency factor A based off of what the y-intercept looks like. Another common kind of more simplified version of this equation can be seen right here. This relates specifically just to rate constants at 2 temperatures. So maybe you don't have like, say, enough data to complete like, a full plot or anything, but you really only need 2 points to make a line. So let's see an example of using this like 2-point Arrhenius equation. So consider here, I have this reaction of hydrogen iodide decomposing into hydrogen and iodine gases. For this reaction, I went and found 2 different rate constants at 2 different temperatures. The first one is at 500 Kelvin. The rate constant is 9.51 times 10 to the minus 9 per molar per second. And then the second rate constant is at 600 Kelvin, and that has a rate constant of 1.10 times 10 to the minus 5 per molar per second. And so here I want us to determine the activation energy in units of kilojoules per mole. You can go ahead and pause and then take like a couple minutes to think how you might apply this equation with these example rate constants. And then in the next slide, I'll go through and kind of walk through all the math of it. But so take a moment to try to work this one out on your own, and then you can unpause when you're ready to see the answer. All right, so I would set this up by, again, using this like 2-point Arrhenius equation where I have my 2 K constants, my 2 temperatures, and from this, I'm going to solve for the activation energy. So in using the information provided, right, I'm just going to basically assign my 2 different K values and my 2 different T values. It doesn't necessarily matter which one you say is, say, T1 or T2. It just matters that the K1 goes with the T1. So for instance here, when I see like 9.51 times 10 to the minus 9 as 1 K constant, the corresponding temperature with that is 500 Kelvin. So maybe just for the sake of this example, I'll define those as K1 and T1. But again, if you did this with, say, the other rate constant and other temperature as subscript 1, it would work exactly the same, just as long as they like match up together. But so placing those things into my equation thus far, right, I have the following setup. Again, the R constant here is the universal gas constant of 8.314 joules per mole Kelvin. So I included that in my calculation as well. Now I'm just going to kind of walk through the math a little bit like step by step. Usually I don't like taking equations like this and trying to solve them just all in one go. I try to like break it down into little pieces. So say first, right, I might go ahead and solve for whatever this fraction is of the K2 over K1. I find that that piece alone equates to 1,156.7. So I just kind of replace that into my equation and kind of start simplifying it like step by step. Similarly, I solve for the like 1 over T1 minus 1 over T2 individually as well. So I have kind of the steps worked out here as well. So showing my work, right, this is kind of the next step that I would get to in my calculation. From here, I can continue to evaluate this out, taking the natural log of 1,156.7. I get then 7.053. One thing to note about significant figures when it comes to logarithms, it's a little bit different than just the normal sig fig rules that we're kind of used to when it comes to like multiplication and division or addition and subtraction. So for sig figs that are part of a logarithm or part of an exponent, the rule goes as follows. Basically, however many significant figures are, say, inside the logarithm, that's how many decimal places you would report your answer to. So because we took the natural log of a 3 sig fig number, my answer is going to be, doesn't necessarily matter how many sig figs, but it's going to be 3 decimal places in. So that's why I report it here as 7.053, right? So to that 3rd decimal place, that matches the 3 sig figs going into the log. We're going to be doing actually a lot of logarithm-based calculations in some of the later chapters as well, so you'll kind of get used to this rule. But this is just like an additional significant figure rule as you are working through anything that involves logarithms or natural logarithms too, has the same rules applied to it. But so, right, coming back from that though, again, I have here kind of my work thus far. I'm also taking care to manage my units throughout this entire equation, right? As far as the k divided by k portion, the units are just going to cancel out. So those kind of disappear, once we run that fraction. But for the units of like temperature, right, because that was the absolute temperature, those were in Kelvin, we can see kind of how the units cancel out at each step of this calculation. And so I just kind of show those as well. And so solving for activation energy, I find that it's equal to about 175,000 joules per mole, or putting that into the proper units, about 180 kilojoules per mole. But so again, this is kind of like how we can use that like two-factor Arrhenius equation to solve for the activation energy. Again, some of the other variations on the Arrhenius equation are more applied to if we have like a larger set of data to pull from. But if we do just have like two rate constants at two different temperatures, this is how they can be related to one another. All right, but please let me know if you have any questions, and I'm always happy to help. Bye.